problems with the homework that we need to look at? Do you understand how to find those contours? You can match those graphs up? Nope. You can't match those graphs up? Wait, just a minute, I hope I have this on here. 14, is it 14.1? Is this it? Oh, you can't see. Yeah, of course. Just a sec. There it is. 14.1. Did you, was there matching? Oh yeah, there was matching. Is this the matching? 32. 32 is matching? Oh yeah, there it is. 32. Wait. Still looking for 32. Oh, there it is. Finally found the matching. All right. So this was hard? What was hard about that? Okay. Hey, let's get some hints. Let's see how we're going to figure this out. You know my deal is with matching, you use process of elimination. Pick off the easy ones first and then go from there. So let's see. What do we got here? Right here, let me just, I'm not even looking at the functions right now. Right here, we got something, this looks like it's sine or cosine. Sine or cosine maybe, question mark. Let's see, this one, what in the world is that? Oh, what's that? What, am I doing the wrong one? I'm good? Okay. So this one, we got a hump in the middle. Hump in the middle. And nothing, it gets low on the outsides. Ooh, that might be a sine or cosine as well. Okay, this might be sine or cosine. Sine, cosine. I'll put a question mark. So we're gonna find out. Ooh, this one is interesting. That one has ridges. Ridges. So intersecting ridges. So once I've looked at these intersecting, whatever, ridges, you see the ridges like here, there's a ridge, and then it's like flat and low on the other points. So it's like two mountain ranges that intersect maybe. Okay, now let's go look at these things. Oh, there's some cosines and sines. So I'm guessing that those two correspond with the two that I labeled sine or cosine. Okay, so let's see if we can distinguish these. For this one, when x is constant, y, you have a sine or a cosine, right? And when y is a constant, you have a sine or a cosine. I guess the same is sort of true here, but this one down here looks more like the sine or cosine is moving outward from the center, so that it's sort of constant. You have the ripples in a pond. I think I've got one of these out here that looks like this. So I'll just make quick work of this. So this one, if you let x be a constant, you pick a constant like the constant 1, then you have the cosine of y. If the constant is 2, you have the cosine of 2y. So I'm going to go with f as being this one right here. Where is it? That one. This one I'm going to go with letter f, or maybe is that Roman numeral 3? Whatever. However you want to match these up. And then the other one I'm going to go with d. There, by the way, the reason why that's d I know for sure. Wait, how are these numbered? That's Roman numeral 5, isn't it? So that's Roman numeral 5. The reason I know for sure that that's the way that is if you think about it, this looks like the cosine of r, doesn't it? The cosine of r, back in your days of knowing about polar coordinates, r is the square root of x squared plus y squared. Why can't they put parentheses around these? Have I complained about that? I probably have. Okay, but anyway, the cosine of r, and so as the radius goes out, no matter what direction you go, you're going up and down on the humps. Okay, so that takes care of that. Let's see, does anything here, this one and that one both look like they might qualify as having a hump in the middle? And the reason I say that is because notice when x and y get big, both of these end up getting small. So when x and y are big, both of these flatten out, and they could have a hump in the middle. So let's see which one of those is which. Let's see. One of them will be I, and one of them will be, or Roman numeral 1, one of them will be Roman numeral 3. So let's see which one is which. Let's see, when x equals 0. Oh, this one is the ridges. And the reason is that when x equals 0, this is just 1. So along that 1, when x equals 0, you have that ridge of 1, and when y equals 0, you also have a ridge of 1. So that's the intersecting ridges. So that's this one, Roman numeral 1, and the Roman numeral 3 is the other one. So this is going to be Roman numeral 1, this is Roman numeral 3. That leaves us just with two to worry about. And let's pick on the natural log. Natural log gets bigger, but it gets bigger at a slow rate. And so here's what natural log looks like. So let's see, does anything look like that?
3 on there twice.
What?
Yeah, I think the bottom one is supposed to be.
Oh, because this thing is. Oh, this is Roman numeral 2. Okay, that's so that one should be Roman numeral 2. Sorry about that. Okay, so I don't know this one. Okay, let's go with this. This one's easy. This is going to be this thing, and the reason I know that is because of those two. Notice that x times y, when x times y is 0. So when x is 0 or y is 0, the function value is 0. So you have that situation there. So we'll go with that in process of elimination. The other one is whatever's left out. Is it Roman numeral 2? No, it's whatever's left. 4, IV. It's 4. We'll go with that. So anyway, yeah, so it's hard. I have something similar on my quiz here, but I've made it really easy, I hope, because, for example, there's one of these that is a plane, and there's only one picture that is a plane. Match them up. One of these is, yeah, you'll see. I made it super obvious, not as difficult as this. So that's that. Was there anything else? Can you make the contours? Do you understand what this means? You can make a contour map, can't you? Because I got that as my second question. So matching, make a contour. Sure, you can do it. Let's give it a go. Let's see. So let's try this out. 1, 2, 3, 4 for you. Let's do 4 for you. 4 for the back. Oh no! Look at this. Everyone's throwing papers. Okay, don't worry. There's one more just to be sure. There's stack them up. Crumple. Here's 4. 1, 2, 3. You want one more? Okay, there's a bunch. Here, I know you guys want these. Ooh, I gotta yell at you people for something you did on the last quiz. So remind me to do that before you leave. Did everyone get one? Who wants one? How about people who don't want one? Stack it up here. Is this the stack? Okay, for the video watchers, I'll get it up here in just a second. Let's see. There it is. By the way, if you prefer looking at color, if the color helps you, I've got the color versions on the screen. Ignore the stuff to the right, the ones on the left. And it's A, B, C, D. I guess they didn't really show up very well. My letters, I should have put them elsewhere on the graphs. All right, don't get too fancy with me on that last one. Just you'll see mine is definitely not fancy. So pick a few numbers, make your little curves, and call it a day. Yeah, don't feel like you got to make it perfect, because yeah, when you see mine, mine's a joke. It's really bad, but it gets the it gets the idea across. Let's just say. So. Yes. All right, if you are done, feel free to send that thing over towards the middle here, and I'll come get it. If you aren't done, maybe you can put a few curves on that picture. See how you did. Nice. I love these. I see some curves. I love them. Nice. You got a lot of curves. Got some curves for me? Fascinating. Wow, this is really interesting. Curves are certainly curves. Curves over here. Wow, so interesting. There is consistency, let's just say. So, we are consistent with nothing else. Oh, is there another number here? 8 or something? Sorry about that. Very nice. There's this. A few more. You have some curves. Those are curves.
That doesn't sound good at all.
All right. Don't shoot for perfection. Yeah, I'll give you another minute, and then we'll get going. Let's see. Quiz, there it is. Okay. Oh, I love it. Oh, yeah. Okay. Very nice. Those are good curves. All right, do I have all the curves? I think I've got all of them. All right, before I reveal the answer, I need to yell at you about this. So you recognize that. Some of you have taken yours out of my little accordion-shaped thing, but if you haven't, it's here waiting for you. And I was surprised at how many of you failed to do the correct derivative here. So let's just review, okay? R prime of t. I know it's exciting when you see t cubed to say that the derivative is 3t squared. Sure, and everyone got this one right. And then this one most people got right as well. But you see the problem, don't you? We forgot about this right here. So don't forget that constant. I was trying to make it easy on you, and some of you left that, forgot the 1/3. So 1/3 times 3 is actually just 1. So that's just going to be t squared I. So be careful when you're doing your derivatives, because it like snowballed. I know you already know if you were, like yesterday we went over this, but that was the thing that messed up some of you for the whole problem. If you had gotten that at the front end, because it snowballs, you use this over and over again, and then this is the way you feel. Anyway, so I just wanted to mention that. Let's go to this quiz that I just collected. Hopefully I didn't look over this. Hopefully you got these. I tried to make it so obvious. Like for example, f of xy is x squared. You have this nice parabolic, and then the x squared plus y squared. That's this nice paraboloid. The only one that has any sort of undulation is the sine of 2x plus y there, and then the plane. So I told you it was going to be easy. I hope it was. Okay, let's deal with this this thing. Since I don't know, I saw like one or two of you got it right. So let's go ahead and remind you how you do this. So we're looking for contours, and I was like, any 5. I don't care which ones you do. So here's what we do is we take f of xy, and you pick a number. So let's pick a number just a minute. I will let you pick the number. Here, who gets to pick the number? I know you all want to pick one, but Kelsey gets to pick a number. Do you have a number in your heart that you like?
1.
1 is a great number. I love 1, but you could have picked any number. Let's use 1. So you pick a number. So this is Kelsey's number. You pick a number. Pick a number. Okay, whatever. And then now we're just going to write this like this. And you graph that. Graph that. You're like, how do I graph that? I don't know how to graph that. Come on. Do a little bit of algebra here. 1 over x squared. Now you can graph that. Even if you don't know how to graph it, some of you have these fancy calculators that allow you to graph. And you'd say, oh, I know how to graph that. That looks like this. It's this nice curve. Looks like that. Goes off into there it is. So that's the 1. And then you would do the same thing. So you'd pick another number. And you'd be like, oh, I don't like the number 1. I like the number 2. So I got x squared y equals 2. And that gives me this curve right here. So this is the 2. I've got mine in multicolors. I did 0 even. 0 is a confusing one. And if you chose 0 to begin with, that one is hard. Whoops. We do this in a different color yet. So let's say you chose 0. You would have x squared y equals 0. And you'd be like, what do I do with that? Well, you get 2 different curves. You get y equals 0, because if you divide both sides by x squared, you get y equals 0, which is this. That's easy enough. But you actually also get this, x equals 0. And where'd that come from? Well, divide both sides by y, and you get x equals 0. And so that's this. So you get this weird, it's not really a curve, but all along that line, those 2 lines, is sort of sea level. Here you're going up, so you're going above sea level, so you've got a hill. So apparently this is a valley here, and then out here it's like an ocean trench, or not a trench, this is like a sandbar, because it's right at sea level, and then the ocean goes down on either side. Here's my final. That's what it looks like. If you're curious, I just put negatives in there too if you were worried about what happens with the negatives. So here you're going uphill, here you're going downhill into the ocean, if you will, if you want to think of it as sea level. Oh, wow. So, yeah, a lot of you just chose to put a bunch of circles. I guess I was goading you. It's like, put some circles on there. No, I didn't say circle, did I? I just said curves. I'd say these are curves. So many circles. Wow. Okay, well, I guess I'll have to have some, maybe I'll need another latte before I do that. Grade that. Okay, well, let's move on. Today I bring you good tidings of great joy, which shall be to all calculus students. And that great joy is the fact, oh, there's Psalm 117, which also brings us great joy. But it's the fact that we get to go back and do something super simple, and that is derivatives. That's all we're doing today is derivatives. We're going to do derivatives. I know, so much happiness and joy. So today, all derivatives all the time. So the only thing I need to mention is that because there are multiple variables, we have to account for that in our derivatives. But I think you're going to be fine with this. In fact, let me demonstrate that I'm pretty sure you can handle this. Let's take that function from the quiz. So here, let's just go ahead and do this. Let's take the function from the quiz, f. So we have f of xy is equal to x squared y. That's a function. And let's just say that without even explaining what all this symbolism means, let's say that I asked you to do the partial derivative with respect to x. Let's see how we do. In fact, I'll just pick someone out of the blue, and I'm sure every one of you could do this, but Daniel, what do you think the derivative of that function is with respect to x?
2x.
Yeah, 2xy. So here's the trick that you might have not even thought about, that Daniel might have not even thought about when he did this, but when you do the derivative of a function with respect to x, you treat all the other letters as if they are constant. So for example, that y there, it's a constant. It's like the number 5. So if that was a 5, you would say, okay, do x squared is 2x, and then the 5 goes along for the ride. Let's see if you can do the same thing down here. What if I asked you for the partial derivative with respect to y? Let's see if we can do that. I'm sure you can, but Max, what is the partial derivative with respect to y? Yes, very good. So yeah, it's a little bit harder because we're so trained to think of x as being special. But because we're doing the derivative with respect to y, you treat the x as if it were a constant. Like if this was the number 3, you would just do the derivative of y, which is 1, times the 3 squared. So just x squared. That's pretty much it. So here's the rule, is when you're doing the derivative with respect to x, treat all other letters as constants. So you treat them as if they are constants. That's pretty much it. We're done. Oh, no, we're not quite done, but we're pretty much done. That's pretty much it. So I have a bunch of examples and practice for you, and then we have a slight complication that we have to deal with. Let's see, yeah. So let's go ahead. These are boring, but we'll do them nonetheless. Those look confusing, don't they? Here, let me put lines in there. Yeah, why do they look so ugly? Just a minute, can I fix this? Yeah, those are supposed to be partial derivatives. Let's see, I bet I can fix it on here. Hold on a minute. Let's see if I put a space. And then it goes off the screen. Hold on a minute, can I make this smaller? There we go. It's moving around, I realize. It'll come to in just a sec. There it is, it updated. I knew it would eventually. Okay, so we update, if I got to go through the ether to get to the iPad. Okay, so let's go ahead and do these. These aren't bad. And so here again, I was just complaining about our textbook not having parentheses, and here I go, not having parentheses. Okay, I should also, I suppose, explain a little bit something about the notation. So let's just go back for just a sec so that you can understand the notation. The derivative, partial derivative, so this is called a partial derivative because even though this has two variables, we're only doing the derivative with respect to one of them. So we're doing the partial derivative. Partial derivative with respect to x. I know that just looks like a cursive D, but that's a symbol that mathematicians think of as the partial symbol. It kind of looks like the Greek letter lowercase delta, but it's a partial. Partial with respect to x of this function. So that's one way of writing this. Another way is to use a subscript. And if you want to sort of think of this in terms of what you've learned before, back in the olden days, you used to have just dy over dx. That was your derivative. And sometimes you would write that like this, with a prime. So this f sub x is kind of like the prime notation. This is the operator notation. That's what that's called. It's an operator. It's the partial operator. So let's go back and see how we do with the ones that I just had up there trying. There they are. So let me just zoom in on this. Let me do the first couple, and then I know this is so easy. It's hard to even say that it's going to be difficult because, like I said, this is great joy for everybody, I'm sure. So this first one, I'm doing the derivative of each term with respect to x. And I'm going to put a 0 there just to clue you in to the fact that that is a constant, and the derivative of a constant is 0. So I think that the main thing that you have to overcome is the temptation to think of x as being special when you're doing this derivative. So let me go ahead and do that one. Remember, x is a constant with respect to y. So 0, derivative of x squared is 0. The derivative of 2x is also 0. And then the derivative of y squared is 2y. So you see how we just go through and we can clean these up. 2x plus 2, this is going to be 2y. It's not too bad, is it? Yeah, you're not going to have any trouble with this, at least not at the beginning. There will be some complications that we will get to. So let's go to these three, see how you do. Go ahead and try those, and then I have a few more, and then we'll make things a little harder, but not too much. Today is a happy day. All right, Cooper, Stiegel, what do you think about this next one, the partial with respect to x of xy squared?
If you do with respect to x, you get y squared.
Yeah, just y squared. Very good. All right, let's get the next volunteer. You've already volunteered, but Madison hasn't. Madison, what do you think of this next one, the partial with respect to y of xy squared? Just x. So it's with respect to y. So yeah, I'll put the x there because we treat the x as if it's a constant. What's the derivative of y squared? Very good. So x times 2y, which you probably would write as 2xy. Yeah, so treat the x as if it's a constant. If it was the number 5, you would just say, oh, 10 times y. So here it's 2x times y. All right, so it's going to take a little bit of practice, and you'll notice that on the homework it looks a little long, but it's a lot of this. It's going to be quick. It won't take too long. Oh, next one. Let's get this sine. Oh, Darren, what do you think of this sine of xy?
Is it y cosine of xy?
Oh, I love it. Y times cosine of xy. Now, here you have to be extra careful. Just do it this way, xy. Sorry about the mess there. It's hard for me to erase on PowerPoint. But whenever you have something like this, just be extra careful. You're going to use the chain rule. So just in case you didn't get this, think of it this way. Chain rule, you do the derivative of sine. The derivative of sine is cosine. So here's the way I always think of this, is to do this derivative, I get the cosine and leave everything in the parentheses alone, and then multiply by what you get when you do the derivative of the inside. And notice I'm doing it with respect to x, so the derivative of xy with respect to x is y. If that was a 2x, or x times 2, none of you would have trouble. You would say, oh, it's just 2 times cosine of x times 2. All right, so far so good. Does it look okay? Okay. All right, well, we do need to make it slightly more complicated, but not too much. Like I said, today is all happiness and joy, I think. So what does it mean? That's the first thing that we need to make sure that we understand. Well, back in Calc 1, we all know that if f is a function, then f prime could be interpreted as the slope of the graph of f. This is just something that it's common that you know this. When you think of slope, you think of derivative. Derivative is slope. So that's just something that you're familiar with. In multivariable calculus, when you have a function of more than one variable, then it turns out that f sub x, derivative with respect to x, and f sub y, derivative with respect to y, are both slopes as well. The difference is that they are slopes of the function when you're standing at a point looking, in the y direction or the x direction. So you have to orient yourself and you say, okay, are we going uphill or downhill? Oh, I should have pulled up this thing here. Let's go, I need to close this, because this doesn't have my Glacier National Park on it. Let me go find Glacier National Park. Which one is it? Hold on a sec. This one. Where is Glacier? There it is. Oh, that's so good. Yeah, let's look at Glacier. So let's just to interpret this, if you're standing, let's see, let me find a place that's interesting. How about standing right here? Let's do this. So you're standing at that point on the mountain. So if you're standing right there, and this is you're looking down, the x direction is this way, so that's the x direction. So f sub x is your slope in that direction. Now you have to look really closely here that you're on a level curve that is actually this way. So if you walk this direction, just for a bit, I mean eventually you'll start going uphill. But if you walk this direction, your slope is 0 right at that point. So going that way, your slope is 0. Whereas if I go this direction, so this is f sub y, now my slope, I'm going uphill, so the slope would be positive. So anyway, that's just an interpretation of that on there. Let me go back. Let's discard all that mess. Let me go back to the one that I have for today, because I have another diagram. Where is it? Derivatives? There they are. Derivatives. I know you've seen that one before. Let me get back to, here it is. Okay, so on this, no, it doesn't appear. So on this, this is more of a three-dimensional graph, not the Glacier National Park situation, but you can sort of see on here, if I put a dot, let's say that I'm right there at that point. At that point, the x direction, x goes this way, and so my slope at that point looks like it's pretty much 0, doesn't it? Going that way, it's pretty much your level. But the y direction, if I go in the y direction, I'm going downhill. That's this way. And so here I would say that f sub x is probably about 0, but f sub y is something less than 0. It looks like it's a pretty steep slope, -2 maybe? I don't know, I'm just guessing. But it's a pretty steep slope there. So anyway, that's what these things mean. They give you an idea of the slope. Another thing that you're going to have to do is you're going to have to come up with higher order derivatives. So a higher order derivative is like a second derivative. And so here, these mainly just need to look at those two. Well, no, those three. Those three are the most important. But just to explain what these mean, f sub xx means do the derivative with respect to x twice. So do the derivative of the derivative with respect to x. And you can write this like this. That's the same as, all of these mean the same thing. And if you ever didn't know, you probably did at one point, but that's why we write the second derivative like this, is because you're doing the derivative of the derivative, and you're just combining those two expressions like that. So the second derivative with respect to y, it looks like this. Do the derivative of the derivative with respect to y. And then in multivariable calculus, you have something called the mixed second partial derivative. So this is a mixed, it's a second derivative, but it's a mixed second derivative. Technically, the way you read this is you work away from f. So start with f, and you say, okay, I've got to do the derivative of x first, and then y. You might say, oh wait, it's different over here. No, no, no. It's the same over here. Notice that if you start with f, the first thing you do is you do the thing that's closest is x first, then y. So that's the relationship between those two. Let's see if we can do some second derivatives. So let's see. I don't want to do all of these because there's too many. But let us do numbers 1 and 2. Yeah, I'll copy these. Just a minute. Let me zoom in and I'll copy this over to Notability. So I'll just copy 1 and 2 once I get this to work. There it is. Okay, give me a sec. But you can get started with 1 and 2 if you want. You're going to have to do all of the derivatives, basically. So, okay, it's going to be annoying for a sec. Paste. There they are. Okay, that's better. Okay, so I did this way so I could make a chart. It'll be a lot easier for me. Let's make that a chart. Oops. I ran out of room. Oh well. I'll put the mixed second derivative down below somewhere. So we'll have room for the mixed second partial. Okay. Please. All right, let's see how we're doing, because if you know how to do this, it's going to be quick and easy. So we'll start with Briar. Briar, what did you get for let's do number 1 first. What did you get for the first derivative for x?
3x squared plus 3.
All right, very nice. All right, Christopher, what about the derivative with respect to y? Look at that, I even just trusted you, and you led me down the road. There we go. Very nice. Now let's do the second derivatives. Nolan, you know how to do the second derivative with respect to x, don't you? So Briar was kind enough to give us the first derivative.
6x.
Just 6x, very nice. And then, Andrew, what about the second derivative with respect to y?
-6 plus 12y squared.
Very nice. Good job. So far, so good. All right, let's do number 2. I know we have one more thing we have to do with the with this, but I ran out of room, so I've made a new chart. 3 out here. I'll just write this down. 3x squared plus 3. F sub y is -6y plus 4y cubed. Okay, well, maybe we could just go ahead and do these mixed second derivatives. So this is f sub xy. Just so you know what you're going to do is you do the derivative with respect to x first, and then you do the derivative with respect to y of that thing. So let's go ahead and do that one, I guess. Joshua, what do you get when you do the mixed second derivative f sub x then y? So you're taking this thing, doing the derivative with respect to y now. Oh yeah, it's 0. That's okay. Sorry, I misinterpreted your silence for not knowing what it was. It was that it's 0. And so there's nothing to say, right? Because there's nothing there. Very good. Derivative, because there's all you have is x's, derivative is 0. Very nice. Sorry about that, Joshua. Cooper Claggett, what about the other? So the other version, if we start with y first, and then you do the derivative with respect to x. It is also 0. Interesting. Let's go back here and let's do number 2. I'm sure you've done all of these. They're easy. Rachel J., what do you say? What's the derivative with respect to x of number 2?
2xy squared plus 2y.
Oh, beautiful. Perfect. Next, we're going to do the derivative with respect to y of the function. So Tyler, what do you get there?
2yx squared plus 2x.
There's some symmetry there, isn't there? Okay, next we'll do the derivative, the second derivative with respect to x. So Emily, and I keep mixing these up. This is going to go here.
It's 2y squared.
Oh, just 2y squared. So isn't this interesting that the derivative with respect to x, you end up with just 1. All right, let's do the next one. It just has to do with the fact that that's what this function that we started with. Madison, what do you get for the second derivative for y? Almost. Which one?
4x squared plus
I think you're on a different one. Yeah, so here, you can just start with this and do the derivative of this with respect to y. So this is the second derivative with respect to y. So let's focus right on there.
2 plus
So what's the derivative of 2y? Just 2y. Just 2. But the x there is a constant, so it goes along for the ride. So that's going to be 2 times x squared. What's the derivative of this constant with respect to y? 0, yeah. So it's so hard because we're so used to thinking of x as being special. But here, not special. It's just a constant. So yeah, so treat the x as if it were constant. And so it is a struggle. This is going to be just 2x squared because you're going to treat the x as if it's a constant. It might have been easier had I written this like this, maybe 2x squared y. Yeah, why did I not? I don't know why. Did I have 2yx squared? Who told me to do it that way? I forget. It doesn't matter. Yeah, if it's written like that, I think it's easier because you can say, 2x squared y. The y is the thing that's important. Everything else is a constant, so you have a constant times y, derivative of a constant times y. It's just a constant, and so that's why it's just that. And the derivative of this, x gets no respect when you're doing derivative with respect to y. Whew. Okay, let's go back to do the mixed second derivatives. So I just need to rewrite this. This is the derivative with respect to x. And this is the derivative with respect to y. Okay, so I think I've copied those correctly. So now what we need to do is we need to do f sub xy. F sub xy, you're taking this, f sub x, and doing the derivative with respect to y. Derivative with respect to y. So let's see if we can do this. Ryan, you know how to do it, don't you?
Would it be 4xy plus 2?
Very nice, yeah. So 4xy plus 2. And then the next one, we've got one more to do. Let's see, you've done stuff already. You've done stuff. You've not here. You've done stuff. Why can't I find someone new? Well, we'll just go over to Claire. I don't think I've picked on you yet. So what's the derivative of this with respect to x? All right. Ooh, whoa. Interesting. Those are exactly the same. So it turns out that there's a theorem that says that, in fact, the derivative like that is always going to be the same as the derivative like that. So if you have a mixed second derivative, you can do it either way. I should say that when I say always, I mean always as long as you don't have some crazy function. So it is possible to come up with a crazy function that does not have this, but all of the functions you deal with are not crazy. And by crazy, I mean things where you have, I don't know, weird things going on with rational and irrational numbers. Yeah, we don't have to worry about that in here. So all of the normal functions, continuous differentiable functions, this will be the case. Okay, onward. Wait, why did I do that? Oh, yes, I know why I did that, because I need to go back here and get to this. Okay, so we need to do a few more things, and then we'll be done for the day. Oh, we only have 6 minutes? Sure, we can do this in 6 minutes. First thing we need to do is we need to go back to charts like this, and we need to estimate the derivative. So here's my wind chill factor chart. And okay, wait, we've already done that. Hold on a minute. We've seen the car. Okay, if you didn't see the car, let's go back. There's the car. Okay, very nice. I don't know why these are, I must have, yeah, I don't know what's going on. So here's what I really want to do is I want to estimate, let's do this. Estimate f sub, let's see, it's t and v. F sub t at the point, let's just pick 2030. Will that be okay? Okay, yeah, that'll do it. Okay, so, and just so you know, this is f of t comma v. So that's 20 degrees, 30 mile per hour wind, just so you know what I'm looking at here. Okay, so I want to estimate f sub t at 2030. So let's first of all find 2030. Here's 20 degrees, and here's 30 miles per hour. And so this is the actual wind chill. But I want to actually estimate f sub t. So what does that mean? That means the derivative of the function with respect to t. So look at what this really means. If you read this the way that you might, naively, you'd say that's the change in the function value with respect to change in temperature. Okay, so we're interested in changes in temperature and how that affects the change in the function value. Well, I know how to do that. I can take this temperature, if the temperature increases, so imagine the temperature increases from 15 to 25. Somewhere in that increase, you will find the temperature of 20. Well, what's happening to the function values when the temperature changes from 15 to 25? Well, the function values go from -5 to 8. All right, well, let's see, change in function value. So we do 8 minus -5. Is that visible? It is not. It is invisible. Let us try again. 8 minus -5. That's change in function values. So you can actually sort of see the green glowed there. And then over change in temperatures, 25 minus 15. What is that, 13/10? So 1.3. So what does this tell us? It tells us that the wind chill changes approximately 1.3 degrees for every degree Fahrenheit that the temperature changes at this point. Now that will be different for different points in this table. In fact, you probably can find places where the temperature difference is about the same, like right here. When you go from 35 degrees to 40 degrees, the temperature, the wind chill changes by 5 degrees as well. So 5-degree change, 5 degrees. So that would be a 1-to-1 comparison. Let's see if we can do this. Let's do this for this. There we go. So this is, stop it. This is the land around us. And what I'd like to know is I would like to know the derivative of the altitude, so we'll just call this f, with respect to x at the point that we are standing on right now. So this is at the Moore Center. So let's find the Moore Center on here. I'm going to fudge just a little bit, and I'm going to put, well, I'll put it right there. Okay, that big blue dot is the Moore Center. So the derivative with respect to x means how much is the slope, or how much is the altitude changing when I go that direction, if I had to estimate that. Now, I realize that when you look out the window here, the ground is flat. Okay, so really it's 0 right here. But if you go a little bit that direction, it goes downhill, right? So how much downhill does it go? So if we had to approximate, and we say, well, there must be a little bit of a slope that we're on here. The way I would do this is I would first of all figure out what each of these lines meant. And so I think that we're counting by 20s. So I believe that this line is the line 980. So that's 980. And so I would start here at this dot, and I'd go this direction. And unfortunately, there isn't a scale on here, but I'm gonna just make up a scale, and I'm gonna say that that distance there is 100 feet. So I've gone over 100 feet. So my distance, oh, is it time to go? So dx is 100, df is -20, so that's -1/5. Does that work out? So anyway, you'll have both of those things. So you're going to be happy when you're doing derivatives like these, but you'll have a few that are on charts and diagrams. Do your best. I'm sure you'll be fine when you interpret those. I'm going to stop the recording if you want to come whisper something.